Hello everyone, I'm Mukta. Me and my friends are here to guide you through this video. First of all, let's see what people like you and me think about material science.
I don't know much about material science. I came to know first time when I came to IIT.
Material science is about metallurgy, ores, what else?
Chemistry. So these all were the stereotypes and myths people have about material science.
But friends, material science is much more interesting and exciting than you think.
Seriously?
Hi, I'm Tushar and he's Kush.
We'll tell you about various exciting avenues material science deals with.
Nanomaterials,
Biomaterials,
electronic, optical and magnetic materials,
computational material science.
and many more.
Out of these, smart materials is what excites us the most. It is not much explored, but the latest developments are pretty interesting.
Let's have a look at some of these.
The flying ability of birds have always captured human imagination. Birds have an elegant feature that's the envy of aircraft designers, a flexible, shape-changing wing. Air flight started out using a more bird-like wing than we use today, but as planes became bigger, designers needed stiffer material and hinged part for flight controls. Currently, airplanes employ different types of parts to imitate a bird's flight, which disrupts airflow and adds weight, a big loss in efficiency. Imagine all of that shape changing can be done like a bird does, just like bending the wings. The wings can be bended using a smart material in them. It's called piezoelectric ceramic. These materials change their shape in response to an electric charge.
Spider-Man depends on tiny hooks at the tip of his fingers, which help him grab the wall. Can we create a material which will let us do the same? Yes, we can. This comes from an animal named gecko. They have nearly a limitless ability to glide. The most amazing thing is that gecko's feet don't feel sticky to touch. Still, it can stick and unstick with ease up to 15 times a second. Let's figure out what is the secret behind this. The answer is hidden in the sheer number and the design of the hairs in its feet. Geckos have millions of microscopic hairs on their toes, which we can't see with naked eyes, as each hair is about 1/10 the size of human hair. Each hair is branched out as millions of split ends. They can make such close contact with the surface that weak intermolecular forces add up to something strong. They exploit van der Waals forces. When I put my hand on the table, I have an apparent contact area, which is just the surface of the hand, but the real area is about a 10,000th of that. The surface area of the hand is like a molecular mountain range. Only the tips of the molecules interact with the surface. But when a gecko places its foot against the wall, all the branching hair are like a forest, pressed against the surface, and when a gecko climbs, it drags its foot down, bringing not just the tips, but the sides of all those hair against the surface. About half the area of the foot of the gecko is in contact with the wall. Imagine a world in which a robot could climb anywhere and carry out different tasks. The key gecko feature on this robot is the material used for the pads on its feet. They are made from silicon rubber. Tiny wedges on the upper surface of the pad use the same gecko principle of directional adhesion.
Imagine if a material is able to heal itself like we are able to heal ourselves. Can we design materials which can do this? High impact technology offered up a new smart material. Let's see. A standard fuel tank which is used in a military truck, and here is one with high impact technology unique coding called battle jacket. Just one bullet hole will spill a 150 gallons of liquid per hour. This happens so fast, even with the high speed camera running 5000 frames per second can barely see it. Battle jacket goes on in 3 distinct layers. The inner layer and outer layer are the same material, especially formulated plastic which can spread to more than double its size. When the bullet tears through the coating and the tank wall, the plastic stretches around it and then snaps short, leaving just a tiny hole. The thin middle layer does the sealing. It contains tiny plastic beads. They lock down the wound. When we try to move something through water, the resistance is directly proportional to how fast we move it. Twice as fast is twice as hard. But this is not true for non-Newtonian fluids. Like ketchup, unlike water, it thickens at rest and its molecules create a weak structure that resists flowing. The fluid changes its viscosity and thickness depending on how fast you try to move it. Keep the action slow and it flows like a liquid, and hit it hard, then it is solid enough to run over. A typical magnetorheological fluid consists of tiny iron particles suspended in a fluid like oil. When we add magnetic field, the metal particles line up, increasing the fluid's thickness. It can work in devices like shock absorbers. Thus, we can also use it to absorb the seismic wave of an earthquake or dampen the vibrations caused by wings that pull a bridge apart.
This was around the world. Now let's see what the professors and PhD students at IITK have to say about material science.
Materials is the backbone of any technological applications.
So we at material science basically deal with different kind of materials having different properties, how the existing materials can be applied in some specific applications by improving their properties.
Technology as it stands at any point depends on the state of development of the materials. That is where it is. So that way, for any technology or any advancement of society, it is materials is the essence.
And for me, material science would be starting right from the extraction of metals to its source, and then modifying its property through various techniques such as alloying and heat treatment, etc.
So I'm currently working on quantum mechanical positioning calculation for inversion charges in devices.
Was essentially dealing with the design of metallurgical reactors.
I'm an experimentalist. I do material characterization. Over the period, we have earmarked the civilization based on the materials used, like Stone Age, Iron Age, Copper Age, and Silicon Age. That is how it is like.